give it up for Casey Rosenthal. Thank you.
My name is Casey Rosenthal. I work for a small internet company called Netflix. If you haven't heard of us, we're kind of like Blockbuster. The topic I'm talking about today is chaos engineering, which is really exciting because I'm basically introducing a whole new discipline into software engineering, into computology, if you will. Chaos engineering is basically a system for increasing your confidence in a distributed software environment. Netflix, the company I work for, really big into open source software. A good portion of our platform is released open source. One of the components that you may have heard of is Chaos Monkey. I'll give you, for those of you who don't know what Chaos Monkey does, Netflix at peak is about 37% of North America's internet traffic by bytes. So that's a lot of data. Most of that comes out of our CDN, but some of it comes out of a control plane that we deploy on AWS in multiple regions. So what Chaos Monkey does is it constantly runs in the background, and it randomly, pseudo-randomly picks servers out of our AWS installation and just kills them in production. The cool thing about this, we've been running this for about 2 years. It's actually increased our fault tolerance and availability. So it's done really well for us, and it did that mostly by aligning our developers toward building their infrastructure in such a way that they can anticipate that servers are going to disappear. And so, now the service is just okay with that. We have a couple other chaos projects under that umbrella. And so 2 quarters ago, I was thinking, okay, it feels like we're onto something with chaos. So what can we do to create a more formalized model around chaos so that we can continue to push it forward internally, but also evangelize it throughout the industry and get other people also participating in the discipline of chaos engineering. So I'm going to try to persuade you of 2 things. One, that there's a need for chaos in our industry now. And 2, that the foundations that I'm going to lay out later for what chaos engineering is are good principles for a foundation for this kind of development. So we'll take a step back for a second and look at where things were and look at this character. Everybody here hopefully knows what an architect is. Architects are cool. Nothing against anybody who's an architect. But in traditional software, an architect generally maintains a mental model of an entire system and then helps guide engineers, right? That's kind of the job description for a software engineering architect. And what I've noticed is that in the industry, we're moving away from having this role. In fact, at Netflix, we don't have architects. We just have senior software engineers. And by working to make their component of code the best that it can be, they don't need architects, and the development of the product is controlled by like an invisible hand, right? So we're making a couple of assumptions. One is that we're getting to the point where software is so complex that no human can hold the entire mental model in their head at a given time anyway. So it's really hard, if not impossible, at this stage in software development for us to have architects. But we're also making a conscious decision, which is that we're trading off on the comfort of having an architect to instead have more velocity and flexibility in what we build by empowering the engineers to build the things that they want to without going through an architect. Okay, I hope that makes sense. That's a trade-off that we're, again, consciously making, but it does take away some of the order, some of the comfort of having an architect. That combined with other industry trends leads to an explosion. Oh, sorry, not that kind of explosion. This kind of explosion, an explosion of complexity. I'm just going to tacitly, explicitly assume that all of you agree with me that as a whole, our industry is getting more complex, from microservice architectures to any loosely coupled design paradigm, reactive systems, message-based distributed systems, containerization, so now anybody can deploy directly to production in a matter of seconds instead of minutes or hours or whatever your cycle was previously, continuous deployment. Stuff is getting more complex, and that's really scary. It's not scary. It's flowers, right? It's beautiful. It's not scary. But it does create some uncertainty. So chaos engineering is designed to reduce that uncertainty, add confidence in these systems that we build. I'm going to quickly give you a taste of the kind of complexity that, that I'm talking about here by taking you through what's called the beer game. There's actual beer tonight, so you're not going to get drunk during this presentation. I'm not, well, maybe. So the beer game, if you've pursued an MBA and you've taken a systems thinking class, maybe you've been through the beer game before. If you're thinking of getting an MBA, I'm ruining a semester for you. So we're not actually going to play this. I'm going to take you through what a typical game of the beer game, typical game usually looks like. So usually a class is divided into 3 teams: customers who like to drink beer, retailers, they get to sell beer, and manufacturers, microbreweries, they get to make the beer. And these 3 teams can only communicate to each other through slips of paper that say what their intention to purchase is from the next person up the chain. Okay, I'm going to have to, this is a live presentation of chaos in action. The font got screwed up, so this table's all out of whack. But I will just fill in the numbers for you, and you're going to have to use your imaginations. The yellow column is the customers, the green columns are the retailers, and the pink columns are the manufacturers. So a customer, a steady state is a customer wants 1 case of beer a week. So they go to the retailer who has 2 in stock. They buy one, the retailer's left with 1. The retailer orders 1 case of beer from the brewery. Okay, that's steady state. But in, so that's say week 0. So in week 1, something weird happens. Elvis comes out of retirement, and he wants to celebrate, so he goes to get some beer, and he orders 4, but there's only 2 in stock, so he can only purchase 2, and that gets passed to the retailer, to the microbrewery, and so on. And then he throws a bigger party because he decides he likes this beer so much, let's call it Graceland Lager, that he writes a song about it. And he invites his friends over, and they want to order 16, but they can only purchase 4 because there's only 4 in stock at the retailer. And again, the retailer passes the order on to the microbrewery. And then the song starts to take off in the town, right? In presumably here in Nashville. And so now 64 people want to buy cases, but they can only buy 8 because the retailer only has 8. So there's this missing demand, this remainder demand of 56. And the retailer's completely out, but they see hockey stick growth. So they're like, oh, we're going to start manufacturing 250 cases a week. Then somebody realizes, hey, Elvis, if he were alive today, he'd be like 80 years old, and this guy's like in his 30s, so clearly he's not Elvis. So while that news is breaking, people still want to order this, but there's none left in the store, so there's this missing remaining demand of 52. The manufacturer's all out. And then the next week, the only person who wants to buy the beer is this Elvis impersonator, but he can't because, again, the store is still out. But the manufacturer now has a new microbrewery online, so they have 250 cases of it. And the last week, we're back to steady state with just 1 being purchased. The retailer has more cases of beer in stock than they could possibly ever sell in a year. A lot of missing domain, remaining stock, and the manufacturer is also left with a bunch. So we end up with these results. Customers who were not particularly happy, retailers who are way overstocked and missed a huge amount of potential profit, and a manufacturer who is also way overstocked and now has an extra factory. What the heck are they going to do with that? Okay, so what do we learn from a game like this? Well, the interesting thing is all 3 of those players, the customer, the retailer, and the manufacturer, they were all behaving exactly rationally. They were all making the right decision given the information that they had, and yet we ended up with this really undesirable result. The analogy here is if we're in a microservice architecture, or we're in a decentralized development environment, all of our libraries, all of our services might have full test coverage, right? From unit test to end-to-end test, everything is golden and passing. They are behaving exactly as intended. However, in the aggregate behavior of the system, we get a really undesirable result. That's the kind of thing that chaos engineering is trying to attack heads on. That uncertainty, that potential for a systemic failure. Testing does not address that. So, I'm going to propose 5 principles that chaos engineering is founded on, and hopefully from this enthusiastic open source community I can get some feedback on. So chaos engineering, first principle, keep it real. I almost said that with a straight face up here. Chaos engineering is a series of experiments, and the variables are real world variables. So they're things that could happen in real life. Thank you. Perfect example of chaos in action, right? So this whole presentation has been an experiment, and thank you, Casey. And at any time, she could have thrown this at me, and I had no idea when she was going to do it. But that's exactly the kind of real-world effect that I'm talking about. It doesn't matter what the integrity of your engine is if we throw a pothole in front of you. Okay? Examples that we want to use: servers disappearing, backhoes cutting cables, hard disk going bad. Not always bad things. Huge increases in traffic, huge increases in latency, errors. We could spend all day coming up with interesting things that we can introduce as variables into the series of experiments. T-shirts being thrown at you while you're on stage. All of these are outside of the scope of the logic of the algorithm that the engineers are writing. Okay, so this is not testing. Testing is the domain of correctness, or covers the domain of correctness, where you have an environment and you insert some conditions and assert that it does what you want. Chaos engineering is about running an experiment where you have an environment, you change some variables, and you don't necessarily know what you're going to get, but you know what to look for. It's a hypothesis that you want to refute. Second principle, request paths. We focus on request paths, not code paths. And this is why. We're making an explicit assumption that the system is getting too complex for an architect to hold a mental model of the whole thing in their head. So, by the same token, we assume that QA, testing, the engineers writing this, they also cannot predict accurately what the user will do with that system. So the only way to get around this is to test the request path and not a code path, which means taking live traffic. Historical traffic won't work. I'll leave that as an exercise for you guys to figure out why. But you have to run this on production traffic, which makes it so much fun. Third principle, measure steady state. So steady state is like your guiding star for a chaos experiment. And this can be complicated, figuring out what steady state means for your business case. Looking for something that in some cases isn't there. But it's an explicit trade-off that we're making. It's a conscious trade-off we're making to say, okay, the number of transactions per second that the site is supposed to handle, or the number of movies being watched per second or something. That steady state, we have to fingerprint that as the health of the system, and the experiments have to focus on measuring that as the metric of import. This keeps us from focusing on things that are outside of the realm of chaos, like how does this model work? If you're investigating something, that's an investment in your time. And how the model works might be really interesting and it might be necessary if you're fixing bugs, but that's outside of the realm of chaos engineering. So for chaos engineering, we have to focus on measuring the steady state of the system. Run continuously. I'm not going to say why. Again, I'll leave this as an exercise, but chaos exercises have to be running all the time. And the fifth principle is machine intelligence. So the analogy I like to use here is chaos engineering can't simply build a better broom to sweep up the floor and then ask people to sweep. We need to build something like a Roomba. Ignore the animals. I swear this is the only picture of a Roomba I could find on the internet. But between fingerprinting the health of the system and knowing, having the automation to run chaos exercises constantly, have it correctly parameterized, and learning from its own previous experiments, you're going to need machine intelligence to pull off an ecosystem of chaos successfully. You can't just do these as one-off manual things. So to summarize, the 5 principles: variables reflect real-world effects, not algorithmic or logical correctness. We want to identify the request interaction in production. We want to measure steady state, not models, not other effects. We want to run experiments continually, and machine intelligence is required, and I'm arguing that that makes a foundation for chaos engineering that I hope is an industry phenomena in 2015, 2016. That's chaos engineering. I'm Casey Rosenthal, Casey the Lesser, and I would love your feedback. I'm not above bribing you, so I have Netflix gift certificates. The best question, comment, or criticism that comes from a human or robot, I'll give you a Netflix gift certificate. Thanks.
All right, I mean, does anybody have any questions? There's a gift certificate on the line, so. And as I said before, Netflix is super awesome, so I've already endorsed it.
Woo!
Okay, maybe, oh, yep.
Do you guys create some chaos that's not like a failure, but more blatant behavior?
Aside from chaos, Netflix constantly runs A/B tests to try to continuously improve the user interface. So that might be more like what you're talking about. But in chaos, there's no reason why we shouldn't also do things like threshold testing, where we say, hey, what if there's, we release the season of Orange is the New Black, and all of a sudden we have a huge surge in traffic. Let's test that kind of thing, which isn't a failure. That's a good condition, right?
Okay.
Can't let Daredevil ever stop.
Also, one more thing.
Why don't you introduce a new failure mode into the chaos system so that you don't accidentally take out production?
So you don't accidentally take out production. Who says that's a bad thing?
It might be fun.
I think that the experiment, you would have to look at it on a case-by-case basis. So, for example, we have what we call Chaos Kong, where we fail out an entire region. In non-Amazon terms, that's like an entire data center. And we move all the internet traffic over to another region. And without telling Amazon, they don't like that. Fun fact. And in that case, we know things are going to break the first time we did it, and we just have to go, okay, it's going up, something's broken, roll it back. Move all the traffic back to that data center. And then fix those, and then it took a couple tries before now we run that kind of exercise routinely. So it's definitely, there's definitely something outside of a principle that is in the context of the kind of experiment that you're running that would determine how you would safely do it. But sometimes users are affected. And we believe that a small effect on the user that we can control for the sake of the health of the entire ecosystem is right now a trade-off that we're willing to make. Is there another question back here? That's a pretty good question.
Okay, great. Thank you so much.
Okay, cool. I'll be around.